a number of reactions that we've talked about throughout the course have been actually operating by a radical mechanism, and we've sort of skipped over those mechanisms, but now we're going to discuss some of these reaction mechanisms more in depth, and they'll help us explain why we get certain reaction outcomes. So one of the reactions we sort of skipped over earlier in the course was the reduction of alkynes using sodium in ammonia. And so just to remind you what the overall transformation was, we took an alkyne, and in the presence of sodium metal in liquid ammonia, we ended up forming an alkene, but it's a trans-selective alkene. Okay? So the mechanism of this involves a radical mechanism. Okay? So let's go ahead and go over that mechanism. So we have our alkyne here, and we're going to react that first with sodium metal. And you can think of sodium as neutral. This is sodium metal, where it's neutral. Sodium metal has an unpaired electron, and so it's able to have that electron be added to the triple bond, and we're going to form an intermediate. So here, we're going to add that single electron to our triple bond, so we're going to break one of the pi bonds in order to do so, and we're going to pair it up with on one carbon, and the other carbon ends up with an unpaired electron. So in this case, we're going to form our transalkyne. One carbon will have a lone pair and a negative charge. The other carbon will have a radical, right? And of course, sodium is now sodium plus, so we have a counter ion. Okay? In the next step, we are going to react our molecule with ammonia, right? And ammonia is going to act as a proton donor, so it's going to act as an acid. So in this case, we're going to do a proton transfer, so our anion that we just generated is going to react with ammonia, going to abstract hydrogen as H+, and NH2- will be our conjugate base. So our product of this, we will now have a new carbon-hydrogen bond, and the other position will still be a radical. Okay? And we're going to repeat this process over again. So we're going to use another equivalent of sodium metal, and this is going to act as an electron donor, right? So we're going to add that electron to our unpaired electron on carbon, and so the result of that will be another lone pair on carbon. We formed a carbanion with sodium as our counter ion. Okay? And then again, in the next step, we're going to do a proton transfer where ammonia is our proton donor. So here, our lone pair abstracts a proton. We generate NH2- as our conjugate base. And that results in our final product where we have the transalkene. So the question looking at this mechanism is, why do we form the transalkene? So it goes back to this very first step where we put the first electron in from sodium. We're going to form two regions of electron density. And so we want to point these sort of away from each other, because if we formed the cisalkene instead, right, where we had a lone pair on one carbon and a radical on the other, we essentially have these regions of electron density relatively close to each other in space. So by positioning on opposite sides of the double bond and trans, right, we're helping stabilize this structure. So this structure here is too high in energy for the reaction to take place. Right? So going through this intermediate here is what ultimately leads us to form the cisalkene.